In this video, we will present blocks and minimal polynomial. Okay? Now, I would like to say that it's worthwhile to say that these topics will not help to solve what we call the objective of all these videos, okay, is AX is equal C. This is a system, system of linear equations. And then we use a Jordan form to solve this system. Now, I will show the blocks here, and it's worthwhile for you to memorize them. It's not difficult. Okay. Consider a matrix A. This is lambda. Okay. A matrix B is lambda, and let's put Q. This is C, is lambda, Q, and Q. This is 0, okay? 0, 0, 0, and 0. Now, D is lambda, Q here, Q, and Q. And so on, okay? Now, let's write what is A minus lambda I. This is just one element. This is equal to 0, matrix 0. This B minus lambda I. 0, 0, 0, and Q. Now, this is C minus lambda I. This is 0, 0, 0, Q. I'll put this is 0, 0, 0, Q, and Q. This is D minus lambda I. 0, 0, 0, 0, Q, Q, and Q. Okay? Now, this is my diagonal, and this what you call super diagonal. Q is real, different from 0. Now, let's square this matrix here. B minus lambda I square is equal 0, Q, 0, 0 times 0, Q, 0, 0. The result is first row, first column, 0. Second row, second column, 0. Now, first row, second column, 0 times Q plus Q times 0 is 0. Now, second row, second column is also 0. What you see here is this. This square matrix, 2 by 2, 0, 0 in the diagonal, and 0 here, and a real number, Q, different from 0 here. If you square it, you're going to get matrix 0. Now, let's do this. C minus lambda I will square it. I repeat, 0, 0, 0, Q, Q, times 0, 0, 0, 0 here, Q, Q. Let's square it. Let's see what it's going to get. Now, here, first row, first column. Don't forget, okay? This column is 0, okay? Now, first row, first row, first column. This will be 0. Second row, second column. Look, 0, okay? 0 here. And 0 times q. Okay? Plus 0 times 0. Plus q times 0. So this will be 0. Now, this third element, third row, first column. Third row, first column. This will be 0. Now, the second column here, okay, first row, second column. 0 times q plus q times 0 plus 0 times q is 0. Now, this element here, second row, second column. Second row, second column. 0 times q is 0, 0 times 0, and q times 0 is also 0. Now, third row, third column, also be 0. Now, third column, okay? First row, third column. Look, 0 times 0 plus q times q. Plus this is q squared. Second row, third column. Second row, third column. 0 times 0, 0 times q, and q times 0. This is 0. And the third row, third column is 0. Now, this square matrix, 2 by 2, okay, squared is 0. But this is not. But, if you put this to the power 3, this is equal. Okay, this is to the power 2, okay? This power 3, I'm sorry. This is the power 2, I'll repeat this. 0, 0, q squared, 0, 0, 0, and the last row is 0. To here. Times c minus lambda I, which is 0, 0, 0. Now, q here and q here. Okay? So this is c minus lambda I squared. To the power 3, I'm sorry. Now, this is a square, okay? Then this is square times c minus lambda I, it's here. Okay, let's see, I'll put the answer right here. Now, let's fill this with zeros. Now, here, first row, first column. First row, first column will be 0. Now here, second row, second row, first column, also 0. Here, okay, third row, first column. Third row, first column is 0. Now, this column here, okay, this element here, okay, is first row, second column. First row, second column. Look, 0 times q plus 0 times 0 plus q squared times 0 is 0. Now, this one, second row, second column. This will be also 0. Now, third row, second column is 0. Now, the third column here, first row, third column. Look, 0 times 0 plus 0 times q plus q squared times 0 is 0. Second row, third column is 0 and 0. What you have seen, okay, if I square this matrix, if I take the power 3, this is to the power 3 of this matrix is 0. Okay, I will raise here, okay, and I put this answer right here. Okay, I'll raise here. Don't forget, this is 3, okay? Now, this to the power 3 is equal 0. Okay, this is a good exercise for you. You just be d minus lambda I to the power 4, okay? This is be 0. You can do this. Or if you want, you take A, B, C, D. You take this matrix, you put 5 here in the diagonal, and put here Q, 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 and Q. Okay? Then you put E minus lambda I. This will be all zeros. Okay? You take the power 5, you're gonna get 0. That's a good exercise. Now, what you have seen is this. This is 5 by 5. You have in the super diagonal only 4 Q's. Okay? Because look, I cannot put Q here because otherwise we would have 6 columns. Okay? No Q here. Okay, the number of Q's here are always the dimension 5 by 5. 5 minus, okay, 1. Okay, look, this here, okay, is a 3 by 3. 3 by 3. I have 2 Q's. Here is 2 by 2. I have 1 Q. Okay? This is a very, very important result. Consider a system, okay? Now, this system, I'm not solving this system. I just put there to remind you that every time I work in the matrix A, okay, I always think that this A, this matrix, came from the coefficient of the unknowns of a system of linear equations. That's it, okay? Now, so consider A. Consider matrix A. From here. Now, the eigenvalues, I just impose determinant to be 0. Suppose f of lambda is equal lambda minus 2 to the power 3, lambda minus 5 to the power 2. Suppose I have the multiplicity of lambda is equal to is 3, and multiplicity for lambda is equal to 5 is equal to 2. That's what we used to call the symbol as alpha. Now, suppose from matrix A we have a row of A minus 2i, okay? Now lambda is equal to, this is equal to 0. So this is called characteristic polynomial. Characteristic polynomial. Okay? Now, suppose rho is equal, let's see, suppose rho is equal, let's put 3 here. Suppose rho is 3. Okay? Nu is equal n minus rho. What is n? Look, n is 3 plus 2 is 5. Here's a matrix A, I guarantee you that is 5 by 5. 3 plus 2 is 5. So, n is equal to n is 5 minus 3, n is equal to 2. Now, alpha minus nu is equal, alpha is 3, look, this is lambda is equal to 2, okay? The multiplicity is 3, so it's 3 minus 2 is equal 1. What this means? This here means just I have one generalized eigenvector. For sure, there is no diagonal matrix because I'll be set 1 in the super diagonal. 1 in the super diagonal. Okay? Now, what this means? This means two solutions two solutions of a minus 2ix is equal to 0. So I know when I solve a minus 2ix is equal to 0, this homogeneous equation, I will find two solutions or two eigenvectors. Okay? Now, and also two blocks. Now is an appropriate time to talk about these two blocks. Look, J is equal. From here, okay, I can write the diagonal, the multiplicity 3, and multiplicity for 2 for 5. 5 and 5. Okay? Now, I will put one here, or one here. Okay? Now, for lambda is equal to 5, let's suppose rho of A minus. You see, I'll put one over here. Now, imagine one thing. J minus y, J minus lambda y, okay, put 2y here, is equal, this will be 0, 0, 0, 0, 0, 0. Here's 5 minus 2 is 3. 5 minus 2 is 3. Let one be here. Okay? Let one be here. Now, what is the rank? The rank of this j minus 2y. What is the rank of this? Let's count. Here I have one pivot, because these are all zeros. These are all zeros. I have one pivot, two pivot, and three pivot. Look, rho is 3. That's where I put that. Now, suppose I'll have 0 here. 0 here. Now, if j minus 5i, j minus 5i, if I have 0 here and 0 here, let's put here, I have minus 3, okay, minus 3, minus 3. Now, here I have 0 and 0. Okay? So, my row here is, suppose, let's see, 1, 2, 3, row here is 3. Suppose, okay? I didn't write that. I just guessing here, and I was guessing here. Now, N is equal, N is 5, minus rho is 3. This is 2, okay? Then I have two solution here. Now, for lambda is equal 5, the multiplicity is 2. So, alpha minus nu is equal to minus 2, which is 0. I guarantee that there is no eigenvector, generalized eigenvector, for lambda is equal to 5. So there is no one here. I cannot put one here. Okay? If I put one here, okay, rho cannot be 3. Okay? Rho cannot be 3. Now this is 0 here. Now j minus 2i, then I write here, okay, j minus 5i. Okay, this will be minus 3, and here will be 0. Okay, now here will be minus 3, minus 3, minus 3, 0, and 0. Now, this is my 1 over here. Now let's do as follows. How many blocks do I have for lambda is equal to 2? I have 2 blocks. 2 blocks. Let's see these 2 blocks here. Look. 1 block, and this is another block. How many blocks do I have for lambda is equal to 5? Let's change the color. I have 1 block here and another block there. Okay? 2 blocks, I'll put 2 here. Okay? And 2 blocks, I put 2 here. Okay? I'll put red color here. And 2 blocks. You see, I have the 2 blocks. Now, I will do as following. I will multiply this matrix by itself. Okay, I'll square it. I will raise it here, okay, to have a space. I'll raise it here to have space. Now, j minus 2 I squared times j minus 5I. Suppose I want to know this. Now, what is j minus 2I squared? I multiply this j minus 2I multiplied by j minus 2I. So I'll just put here 0, 0, 0, 3, 3. Here's 1, 0, 0, 0, 0. Last one. Let's put it here. 0 here. Okay? This is 0, all 0. And also, this is 0, except this 1. The super diagonal, I have only 1. Let's multiply. Now, here's the block. See the block here? The block and the block here. Now, when I multiply this, I multiply these 2 matrices, okay? This is j minus 2I squared. Now, when I multiply this block times this block, do you remember? Okay, do you remember when I start this video, I have 0, q, 0, 0, square, this equals 0. Remember that? If you don't, just do it this. Very easy. Now, when I multiply these blocks as this, I will get, let's see, I'll put right here. Okay? I have this times this will be 0, 0, 0, 0. Now, here I will have 9 and 9. 3 times 3 is 9. This is 0, 0, now 9 and 9. This is j minus 2I squared. Okay, this is 0 here and 0 there. This is not, there is no 1 here anymore because I multiplied this by this, so my matrix 0. Now, let's do as follows. Let's multiply this matrix times this. Okay? Now, I will erase and I put this matrix here, which is this, times this. Okay? Now, I'll do this because I want to know how much is this. Okay? Now, let's do this. I'll put j minus 2I squared here. I'll raise here. Okay. And here I put 0, 0, 0, 9, and 9. Okay? Now, it is 0 here and 0 there. Times, now I put this matrix here. Let's erase here. This will be -3, -3, -3, 0, and 0, and this is my 1 over here. Okay? This is j minus 5i, which is there. Now, let's see. This is my blue. Let's put here my blue box. Okay, this blocks, and this is my red one. Put it here. Put -3 there. Yeah. You see, this is my red one. This is -3. Now, just look. Just look. Look. J minus 2i squared, okay, times j minus 5i is equal to, you see, this block here, you see this block here, when I multiply by this block here, look, this belongs to lambda is equal to. This belongs to lambda, this is one more 0 here, okay. 3, 0. This belongs to lambda is equal to. When I multiply this 0 for lambda is equal to, for this here, this will be a big 0 here, big 0 here. Now, when I multiply these blue blocks, see, times the blue blocks, you'll be a 0 here. So j minus 2i squared times j minus 5i is equal to 0. Okay? Now let's see, let's compare, okay, the exponent of j minus 2i. This I'll represent this, okay, as this. I can write down here f of a is equal a minus 2i to the power 3. This is a minus 5i to the power 2. This is equal matrix 0. From the Cayley-Hamilton Theorem, which will not prove here, you just open any books or any videos, okay, you listen and see any videos, you see this theorem, okay? Then you have lambda minus 2 to the power 3, here is a minus 2i to the power 3. Lambda minus 5 to the power 2 is a minus 5 to the power 2. The product is always 0, okay? There's a Cayley-Hamilton theorem, okay? Theorem. This always happens. If you get the matrix A from here, attention, and minus 2 lambda I, okay, to the power 3, a minus 5i to the power 2, this is always equal 0. But we found here that there are multiplicity, there are exponents less than these 3 here, and this is 2, this is 1, you see, in which this product also gives 0. Okay? Now repeat. This from Cayley-Hamilton Theorem, we got 0 there. But we found out that if j minus 2i, obviously j minus 2i to the power 3, if this is 0, this will be 0, okay? Because if this is 0, I multiply it 0 times j minus 2i. Obviously, j minus 2i to the power 3 will be also 0. And then, because a and j are similar, you can write here like that. J minus 5i to the power 2 is equal to 0. This is a Cayley-Hamilton theorem. This is f of j. J and I are similar, so I can write this. Now, we found, okay, that there is exponent less than 3, okay, exponents less than 2, in which this product is 0. Then we can go back doing this. Look, doing this. I have m of lambda is equal a minus 2i squared a minus 5i to the power 1 is equal to 0. Now, this is 0 matrix, okay? I'm sorry, just put a here, okay? This is 0 matrix. We found out, okay? We got, okay? Now, this is m of lambda is equal. Now, I will transfer to the scalar. Lambda minus 2 to the power 2 times lambda minus 5 to the power 1 is equal to 0. This we call minimal polynomial. Okay? The minimal polynomial, okay, if you have a minus 2i squared from here, okay, a minus 5i to the power 1 is equal to 0, we don't need, okay, to have a minus 2i to the power 3, a minus 2i to the power 2. That we call minimal polynomial. Why minimal? Because if I put 3 here, also will be 0. If I put 2 here, also will be 0. Okay? Because j minus 2i squared is already 0. Did you understand what you call minimal polynomial?